Good evening. Wherever you are right now, settle into your space for a moment. Feel the quiet presence of the room around you. Notice the air, the way it carries a particular temperature, a certain stillness. There is no need to hurry through this. We are not here for shock or for fear. We are here to engage in a solemn thought experiment, a careful and methodical examination of a force that has shaped the last 75 years of human history. This is an exercise in understanding, not in panic. Our curiosity tonight will be a quiet one, patient and deliberate. We will approach a difficult question not to be overwhelmed by it, but to understand the mechanics that lie beneath it, to see it not as a spectacle, but as a system of causes and effects. It is a way of holding a profound and heavy subject with a sense of calm inquiry, rather than turning away from it. And so, as the world outside settles into its own rhythm, let's allow our minds to settle as well. Let's create a space for a question that is often shouted, but which we will explore in a whisper. It is a question that brings us to the very edge of our technological power and asks us to look, clearly and without blinking, at the consequences. We are going to hold this question gently, not to feel its horror, but to understand its structure, its physics, and the series of cascading events it would set in motion. The question is this: what would actually happen, step by step, if a single modern atomic weapon were to detonate over a city? Our city? Your city? Let's begin this exploration together, with a shared understanding that our purpose is not to frighten, but to comprehend. Before we proceed, it is essential that we establish the lens through which we will view this subject, and the guardrails that will keep our inquiry safe and productive. This is our method, our shared agreement. Our purpose tonight is not to create a simulation of horror. It is to build a conceptual model of a physical event. This is a crucial distinction. We are interested in the physics, the systems, and the cascading consequences, not in graphic depictions of human suffering. Our first principle is one of methodical detachment. We will approach this as a scientific problem. Think of it as a documentary for sleep. The tone will be calm, the pacing will be slow, and the focus will be on the mechanisms of the event. We will use the language of physics and systems engineering to describe what unfolds. This is a deliberate choice to create a space of intellectual safety, to allow us to examine this difficult topic without being consumed by the fear it can understandably evoke. We are building a model, not a nightmare, and a model is a simplified representation used for understanding. It is provisional, based on the best available public data and scientific consensus. It is not a perfect prediction. Our second guardrail is a commitment to avoiding sensationalism. You will not hear dramatic music, sound effects, or emotionally manipulative language here. The subject itself carries enough weight without any added hype. Our tone will be consistently measured and calm. We will use cautious and precise language, favoring technical description over emotional appeal. This is an exercise in sober contemplation, not alarmism. The goal is to foster a deeper, more grounded understanding of the world we inhabit. Third, we will focus on the city as a physical system. We will talk about buildings, infrastructure, the power grid, and the atmosphere. We will trace the flow of energy from the initial detonation and see how it interacts with the built environment. This allows us to understand the scale of the event in concrete physical terms. We are stress testing a system, not imagining a tragedy. This framework helps to keep our inquiry grounded in the material world and its predictable physical laws. Finally, we will proceed slowly, building our understanding layer by layer. We will start with the initial flash of light, then move to the blast wave, the thermal pulse, and the subsequent effects. At each stage, we will describe the mechanism and then explore its implications for the physical systems of the city. We will take our time. There is no rush. Our inquiry is not about arriving at a shocking conclusion, but about the careful, methodical process of understanding each component of the event. So, this is our agreement. We will explore this question as a thought experiment in physics and systems theory. We will maintain a calm and methodical tone. We will focus on the built environment, not on human horror, and we will proceed slowly and deliberately. With these guardrails in place, we can begin our solemn work of understanding. Let's begin where you are, right now, in the space you currently occupy. Take a moment to ground yourself in the physical reality of this room. Feel the solid floor beneath your feet, the chair supporting your weight. Notice the materials that surround you. The walls might be drywall and wood. The windows are glass. The structure of the building is likely steel and concrete. These are the basic components of a modern city. They are materials with known physical properties, a certain melting point, a certain tensile strength, a certain capacity to reflect or absorb energy. These materials are currently in a state of quiet equilibrium. They are subject to the familiar forces of gravity and the slow, gentle pressures of the weather. They feel permanent, stable, solid. Now, bring your awareness to your own body. Feel the air moving in and out of your lungs. Your body is a complex biological system, maintaining a constant internal temperature, circulating oxygen, and processing information from the world around you. It is a system that is exquisitely adapted to the narrow range of environmental conditions that we consider normal. The temperature in your room is likely between 15 and 25 degrees Celsius. The atmospheric pressure is around 101 kilopascals at sea level. The light is within the visible spectrum. These are our baselines: concrete, steel, glass, wood, plastic, fabric, a human body, an atmosphere of nitrogen and oxygen, a world governed by familiar physical forces. We ground ourselves in these concrete nouns, these tangible realities, because they are the very things that our thought experiment will act upon. The event we are about to explore is a story of energy interacting with matter. The matter is the city you are in. To understand the event, we must first understand the stage. Think of your city not as a collection of people or a cultural entity, but as a physical object. It is a dense concentration of manufactured materials, arranged in complex patterns. It is a network of interconnected systems, a power grid, a water distribution system, a communications network, a transportation grid. Each of these systems operates according to its own set of rules and has its own points of vulnerability. This act of orienting ourselves in the physical present is not just a calming exercise, it is a crucial part of our method. By becoming aware of the ordinary physics of our immediate environment, we establish a reference point. This is the before state. From this state of quiet, stable equilibrium, we can begin to introduce a new extraordinary input of energy and trace its effects step by step. So take a moment to notice the quiet integrity of the world around you, the silent strength in the walls, the clear transparency of the glass, the gentle pressure of the air. This is the ordinary world, and it is from this starting point that our thought experiment will begin. Why does it matter to ask this question? Why engage in such a grim thought experiment? In a world where the daily pressures of life are more than enough to occupy our attention, looking at a remote and horrifying possibility can seem like a counterproductive exercise, but understanding this subject calmly and methodically matters across multiple timescales, from the historical to the personal to the future of our species. On a human timescale, in our own lives, it matters because these weapons exist. They are a part of the architecture of our global political system. For decades, their presence has shaped international relations, fueled arms races, and created a background hum of existential risk that has become so constant we often forget it is there. To ignore this reality is not to make it go away. To understand the physics of what these weapons do is an act of civic responsibility. It is a way of becoming a more informed citizen of a nuclear-armed world. It allows us to engage with discussions about disarmament, non-proliferation, and global security, not from a place of fear, but from a place of knowledge. On a historical timescale, it matters because this is not science fiction. This event has happened twice. The cities of Hiroshima and Nagasaki are not just names in a history book. They were living places, physical systems that were subjected to this extreme test. By studying the effects on those cities, we have our only real-world data points. This historical reality grounds our thought experiment. It reminds us that we are not exploring a fantasy, but a demonstrated technological capability. Understanding the history is a way of honoring the memory of those who experienced it, and ensuring that its lessons are not forgotten. Zooming out to a longer civilizational timescale, the question matters because the invention of nuclear weapons represents a fundamental turning point in human history. It is the moment we developed the capacity for self-annihilation. It is a technological threshold from which we cannot go back. The knowledge of how to build these weapons now exists, and it will exist as long as our civilization does. Therefore, the challenge of managing this technology, of preventing its use, is not a problem for one generation. It is a permanent, multi-generational challenge. Understanding the stakes, the true physical consequences of failure, is essential if we are to build institutions and global agreements that are robust enough to manage this risk over the long term. There is no hype needed here. The stakes are self-evident. This thought experiment is not about indulging in morbid curiosity. It is about education. It is about building a stable, intellectual foundation from which to view a complex and dangerous world. It is about replacing vague, movie-induced images of a mushroom cloud with a clear, step-by-step understanding of the actual physical events that would unfold. This knowledge, though sobering, is a form of power. It is the power to see the world as it is, to understand the forces we have created, and to participate in the vital ongoing conversation about how we can ensure a future where this thought experiment remains forever in the realm of theory. As we begin to build our model of this event, several distinct threads of inquiry emerge. These are the different physical phenomena that are unleashed in the moments following a nuclear detonation. We will not explore them all at once. Instead, let's lay them out now as open loops, signposts for the path ahead. We will return to each of these threads one by one to examine them in detail. The first thread is the story of light. The very first thing that happens in a nuclear explosion is the release of an immense amount of energy in the form of electromagnetic radiation, including an intensely brilliant flash of light. A significant portion of this is thermal radiation, infrared, visible, and ultraviolet light that travels at the speed of light. This thermal pulse is responsible for causing fires and burns at great distances from the detonation point. We will need to explore how this energy is released and how it interacts with the materials of a city. The second thread is the story of pressure. In the microseconds after the initial flash, the superheated air and weapon residues at the center of the explosion expand with incredible force, creating a shock wave of immense pressure. This is the blast wave. It travels outward from the hypercenter faster than the speed of sound, carrying with it the destructive force that levels buildings and shatters structures. We will investigate the physics of this shock wave and how it demolishes the built environment. The third thread is the story of radiation. A nuclear detonation releases a torrent of prompt high-energy radiation in the form of gamma rays and neutrons. This is the initial, invisible but deadly wave of radiation. But there is also a second, longer-lasting form of radiation. The radioactive particles created in the explosion are drawn up into the mushroom cloud and then fall back to Earth over a period of hours, days, or weeks. This is fallout. We will need to distinguish between these two phenomena and understand their effects. These three primary threads, the thermal pulse, the blast wave, and the radiation, are the direct, immediate effects of the detonation. They are deeply interconnected, but we will examine them as separate processes to understand each one clearly. They represent the initial violent assault on the city as a physical system. We will return to each of these, tracing their path and quantifying their power. For now, hold them in your mind as the three core components of the event we are here to understand. To proceed with our thought experiment, we need to establish a set of working definitions and assumptions. This shared vocabulary will allow us to be precise and to ensure we are all visualizing the same kind of event. Plain language is our goal. First, let's define the weapon itself. Atomic weapons vary enormously in their power, or yield. This yield is measured in kilotons, KT or megatons, MT of TNT equivalent. 1 kiloton is the explosive power of 1,000 tons of TNT. The bomb dropped on Hiroshima was approximately 15 kilotons. Modern strategic nuclear weapons are often much larger, in the range of hundreds of kilotons, or even over a megaton. For our thought experiment, we need to choose a specific yield. Let's assume a moderate but common yield for a modern warhead. 300 kilotons. This is 20 times the power of the Hiroshima bomb. Next, we need to define the scenario. A nuclear weapon can be detonated in several ways: on the ground, underground, or in the air. For the purpose of maximizing destruction to a city, the most effective method is an airburst, where the weapon is detonated at a specific altitude above the target. This allows the blast wave to travel farther before dissipating. Let's assume an airburst at an optimal altitude for a 300 kiloton weapon, which would be roughly 1,800 meters, or about 6,000 feet, above the ground. Now, let's define the geography of the event. We will use a few key terms. The point of detonation in the air is called the detonation point. The point on the ground directly beneath it is called ground zero, or the hypocenter. The distances from ground zero are what determine the severity of the effects. We will be talking about concentric rings of damage, measured in kilometers or miles from this central point. Let's define the energy release. The immense energy of the bomb is released in three primary forms. About 50% of the energy goes into the blast wave. About 35% is released as thermal radiation, light and heat. The remaining 15% is released as nuclear radiation, 5% as prompt radiation, 10% as residual radiation or fallout. These are approximate figures, but they give us a good sense of how the weapon's energy is partitioned. Finally, we have to make an important assumption. We will model a single, isolated event. In a real-world nuclear conflict, it is highly unlikely that only one weapon would be used. However, modeling a multi-weapon exchange is vastly more complex. By focusing on a single detonation over a generic large modern city, we can isolate the effects and understand the fundamental physics more clearly. We are simplifying the problem in order to make it understandable. So, to recap our working model, we are examining a single 300 kiloton nuclear weapon detonated at an altitude of 1,800 meters over a large modern city. The point on the ground below is ground zero. We will analyze the effects of the blast, 50% of energy, thermal radiation, 35%, and nuclear radiation, 15%, in concentric circles moving outward from that point. These are our starting parameters. With this framework, we can now begin to trace the sequence of events nanosecond by nanosecond. To understand the event, we need a brief, minimal snapshot of the context. We don't need to delve into complex geopolitics, but we need to understand what a nuclear weapon is and how it works, in the simplest possible terms. This background will help situate our thought experiment. A nuclear weapon is not just a bigger bomb. It operates on a completely different physical principle. Conventional explosives, like TNT, release energy through a chemical reaction, where atoms rearrange themselves into more stable molecules. A nuclear weapon releases energy from the very core of the atom, the nucleus. It does this in one of two ways: fission or fusion. Fission is the process of splitting a heavy atomic nucleus, like that of uranium-235 or plutonium-239, into two smaller nuclei. When this split happens, a small amount of the nucleus's mass is converted directly into a tremendous amount of energy, as described by Einstein's famous equation E equals mc squared. This splitting also releases several neutrons, which can then go on to split other nuclei, creating a self-sustaining chain reaction. The bomb dropped on Hiroshima was a fission bomb. Fusion is the process of forcing the nuclei of two light atoms, like isotopes of hydrogen, to fuse together to form a heavier nucleus. This process, which powers the sun and the stars, also releases an even greater amount of energy than fission. Modern strategic nuclear weapons are often thermonuclear or hydrogen bombs. They use a fission explosion as a trigger to create the intense heat and pressure needed to ignite a much more powerful fusion reaction. Our 300 kiloton device is a thermonuclear weapon. The history of these weapons begins in the 1940s with the Manhattan Project, the secret Allied effort to develop the first atomic bomb during World War II. This culminated in the use of two fission bombs on the Japanese cities of Hiroshima and Nagasaki in August 1945. These are the only two times nuclear weapons have been used in conflict. The period after World War II, known as the Cold War, was dominated by a nuclear arms race between the United States and the Soviet Union. Both sides built up enormous arsenals of increasingly powerful thermonuclear weapons, capable of destroying entire cities. This led to the strategic doctrine of mutual assured destruction, or MAD. The idea was that any nuclear attack by one side would be met with a devastating retaliatory strike from the other, ensuring the destruction of both. This created a tense and fragile peace, a stability based on shared terror. Since the end of the Cold War, the total number of nuclear weapons in the world has decreased significantly, but several thousand still remain, held by a small number of countries. The technology has not been uninvented. This is the minimal context we need. We are not dealing with a theoretical device. We are dealing with a mature technology with a specific history that operates on the fundamental principle of converting mass into energy. The 300 kiloton explosion we are about to model is the release of the energy contained in just about 14 grams of mass, less than the weight of 3 nickels. Let's begin our thought experiment. We are at time 0. The detonation occurs 1,800 meters above the city center. The very first thing that happens in the first few nanoseconds is an incomprehensible release of energy. The core of the weapon reaches a temperature of tens of millions of degrees Celsius, hotter than the center of the sun. This creates a small, incandescent sphere of superheated gas and plasma. This is the fireball. The first wave of energy to leave this fireball is not the blast, but a wave of intense thermal radiation. It travels outwards at the speed of light. This is our evidence track Y, the thermal pulse. It is, in effect, a man-made star flickering into existence for a few seconds. This thermal pulse actually comes in 2 distinct stages. First, there is an initial, very brief but intensely brilliant flash of ultraviolet light. This first flash lasts only a few milliseconds. It is so powerful that it can cause temporary blindness in people miles away who are looking in the direction of the blast. This is called flash blindness. The effect is like having an old-fashioned camera flashbulb go off directly in front of your eyes, but on a city-wide scale. Immediately after this first flash, the surface of the expanding fireball is momentarily obscured by the ionized air around it. But then, a second, much longer and more powerful thermal pulse begins. This second pulse lasts for several seconds. For our 300 kiloton explosion, it might last for 8 to 10 seconds. During this time, the fireball continues to expand and radiate an enormous amount of heat, like a gigantic heat lamp in the sky. It is this second, longer pulse that is responsible for most of the thermal damage. Let's trace how this energy interacts with the city. The thermal radiation travels in a straight line from the fireball. Anything that has a direct line of sight to the explosion will be exposed. This energy is absorbed by surfaces, causing their temperature to rise dramatically and instantly. Consider the materials of the city. Dark-colored surfaces, like asphalt roads, dark roofs, and dark clothing, absorb this energy very efficiently. They can be heated to their ignition temperature almost instantly. This is how the fires start. Paper, dry leaves, fabrics, and thin pieces of wood will spontaneously burst into flame. The city itself, with its millions of flammable surfaces, is a vast reservoir of fuel waiting for a source of ignition. This thermal energy is incredibly intense. At a distance of 5 kilometers, about 3 miles from ground zero, the thermal pulse would deliver enough energy to cause severe, third-degree burns to any exposed skin. This happens in seconds. Clothing can offer some protection, but dark, heavy clothing might itself catch fire. The mechanism is simple heat transfer. The implication is a city that is simultaneously set on fire in thousands of locations at once. It's not a single fire that spreads, but a multitude of fires that are born in the same instant, wherever a flammable material had a line of sight to the fireball. This brings us to our first question, the one that hangs over this initial, silent wave of light and heat. We have seen how the thermal pulse ignites countless small fires. But how does this collection of individual fires transform into the single, monstrous entity that is a firestorm? And what does that mean for the city as a system? Now, let's test the boundaries of this first evidence track. We have established that the thermal pulse causes fires and severe burns within a certain radius. But what are the edge cases and complexities? The effects are not as simple as a perfect circle drawn on a map. First, consider the role of line of sight. The thermal radiation travels in straight lines. This means that anything that creates a shadow can offer protection. A person standing behind a thick concrete wall would be completely shielded from the direct thermal pulse. Even being in the shadow of another building could offer significant protection. This creates a complex granular pattern of damage at the street level. One side of a street directly exposed to the fireball might be incinerated, while the other side, in the shadow of a tall building, might be relatively unscathed by the initial heat. This leads to the concept of thermal shadows. After the bombing of Hiroshima, these shadows were starkly visible, permanently etched onto surfaces. The heat flash bleached the exposed stone of a bridge, but left a darker, human-shaped shadow where a person had been standing, shielding the stone behind them. These ghostly outlines are a testament to the immense power and the straight-line nature of the thermal radiation. Next, let's consider the weather. The conditions on the day of the detonation would have a significant impact on the range of the thermal effects. A clear day with dry air allows the thermal radiation to travel with very little obstruction. A hazy or foggy day, however, would scatter and absorb some of the thermal energy, reducing the effective range of burns and fires. Cloud cover could also reflect some of the energy, creating complex patterns of intensification or shielding. The season and the time of day also matter. An explosion over a city in winter, when the trees are bare, would allow the thermal pulse to reach more surfaces than in summer, when leafy trees could provide a significant amount of shielding for the houses behind them. Now, let's stress test the idea of flammability. We've said that flammable objects will ignite, but the flammability of a city is a complex variable. A modern city centre, with its steel, concrete and glass skyscrapers, is much less flammable than a dense residential area with many older wooden frame houses. The density and type of fuel varies dramatically across a city. A fire might start easily in a suburban neighbourhood with lots of dry vegetation and wooden structures, but struggle to propagate in a downtown core made of non-combustible materials. This creates a patchy landscape of fire ignition. The initial state of the city, its architecture, its materials, its vegetation, the weather, acts as a complex filter that shapes the initial pattern of fires. This calm, methodical boundary testing gives us a much more nuanced picture. The initial thermal effects are not a uniform wave of destruction. They are a complex, almost pixelated pattern of damage, determined by the geometry of the city and the conditions of the atmosphere. The world is not uniformly destroyed, it is selectively and brutally edited, based on the simple physics of light and shadow. The implication is that even within the zone of severe thermal effects, chance and location would play a huge role. Survival or destruction, in these first few seconds, could be determined by which side of the street you are on. We have described the silent wave of light and heat, but travelling just behind it, at the speed of sound, is the second and most destructive effect of the detonation, the blast wave. This is our evidence track 2. It is a story of pure, overwhelming pressure. The mechanism begins in the fireball. The instantaneous heating of the air to millions of degrees creates a region of extreme high pressure. This super-pressurized gas expands outwards violently, pushing against the surrounding undisturbed air. This creates a shock front, a wall of compressed air moving at supersonic speeds. This is the blast wave. As this shock front expands, it is followed by a period of intensely powerful winds known as the dynamic pressure. It's a 1-2 punch. First, the instantaneous crushing pressure of the shock front, and then a hurricane-force wind that can last for several seconds. Let's trace the effect of this blast wave on the city's structures. The destructive power of the wave is measured in pounds per square inch, (psi), of overpressure, the pressure above normal atmospheric pressure. Even a few psi of overpressure can have devastating effects. At the centre, within about 1.5 kilometres, roughly 1 mile of ground zero for our 300 kiloton device, the overpressure is extreme, greater than 20 psi. Here, the destruction is absolute. Even heavily reinforced concrete and steel structures are completely destroyed. The blast wave scours the landscape clean. This is the zone of total destruction. Moving outwards, to a radius of about 3 kilometres, nearly 2 miles, the overpressure is still in the range of 10 to 20 psi. Here, most multi-story brick and concrete buildings are destroyed or severely damaged. The immense pressure differential between the outside and inside of a building causes it to collapse. The powerful winds then sweep the debris away. Now, let's go out farther, to a radius of 5 kilometers, 3 miles. The overpressure here drops to around 5 psi. This is still enough to collapse most residential buildings. Wooden frame houses, in particular, are not designed to withstand this kind of lateral force. They are pushed over and flattened. The facades of office buildings are torn off, and the windows are shattered, turning billions of shards of glass into deadly projectiles, travelling at hundreds of kilometers per hour. Even as far as 8 to 10 kilometers, 5 to 6 miles from ground zero, the overpressure is still 1 to 2 psi. This is enough to shatter windows, blow doors off their hinges, and cause significant damage to roofs and non-structural walls. The zone of moderate to light damage from the blast is enormous. The implication here is the systematic, mechanical dismantling of the city. The city as a physical structure ceases to exist in its coherent form over a vast area. The blast wave does not just damage buildings, it reduces them to rubble. It creates an enormous, impassable landscape of debris, several meters deep in the city centre. This has profound secondary consequences. Transportation routes, roads, bridges, railway lines are destroyed or blocked. This makes any organised emergency response from outside the city almost impossible. The physical destruction of the city's structure is the first step in the collapse of its social and functional structure. This brings us to our next question. We have seen how the thermal pulse creates thousands of fires, and how the blast wave creates a vast field of rubble. What happens when these two effects are combined? What happens when a city that is simultaneously on fire is also being torn apart by a supersonic shockwave? The combination of the thermal pulse and the blast wave creates a series of synergistic effects that are far more destructive than either would be alone. These are the second-order effects, the if-then chains that emerge when the different physical phenomena of the explosion interact with each other and with the city. If the thermal pulse ignites thousands of fires, and then, a few seconds later, the blast wave arrives, what happens? The blast wave acts like a giant, malicious bellows. The powerful winds, travelling at hundreds of kilometers per hour, fan the newly started fires, spreading them with incredible speed. A small fire in a living room curtain is instantly spread throughout the entire house. Furthermore, the blast wave itself creates new fuel sources. It shatters buildings, exposing flammable wooden beams, furniture, and paper. It breaks gas lines, creating a source of highly flammable fuel that can be ignited by sparks or the existing fires. It reduces the city to a perfectly aerated, perfectly prepared pile of kindling, and then sets it ablaze. This interaction is the mechanism that can lead to a firestorm. A firestorm is not just a large fire. It is a specific meteorological phenomenon. If enough individual fires merge over a large enough area, typically several square kilometers, the intense heat from the fires causes the air above them to rise with incredible force. This creates a powerful updraft, like a chimney. This updraft then draws in cool air from the periphery of the fire at ground level, creating powerful hurricane-force winds that all blow inwards towards the center of the fire. The result is a single, monstrous, self-sustaining fire that consumes everything within its perimeter. The inward rushing winds are so strong that the fire does not spread outwards. Instead, it rages within its zone until all the fuel is consumed. The conditions inside a firestorm are unsurvivable. Temperatures can exceed 1,000 degrees Celsius, hot enough to melt glass and metal. The oxygen in the air is consumed by the fire, leading to suffocation. Even people in underground shelters can be killed, either by the intense heat conducting down through the ground or by the consumption of all the available oxygen. The cities of Hamburg and Dresden in World War II, subjected to intense conventional bombing, experienced firestorms. It is a plausible outcome for a nuclear attack on a modern city. This sensitivity of the system to the interaction of its parts is a key insight. The demolition of the city by the blast wave creates the ideal conditions for the fires started by the thermal pulse to merge and grow uncontrollably. The implication is a level of destruction that is almost total. Within the firestorm zone, everything that can burn will burn. The city is not just leveled, it is incinerated. This is a powerful example of a nonlinear effect. The combined destruction is far greater than the simple sum of its parts. It is a reminder that in a complex event like this, the interactions between the different effects can be just as important as the effects themselves. As we continue our exploration, it's a good moment to reconnect with the fact that we are in this together. This is a shared space of inquiry, a community of curiosity, even if we are separated by time and distance. I invite you to just notice your location on the planet. Are you in the northern or southern hemisphere? On a coast or deep inland? In a major city or a small town? Each of our locations is a unique point within the vast, interconnected systems of this planet. This thought experiment, while abstract, is ultimately about a real place, a city like yours. Grounding it, even for a moment, in our own geography can make the exploration more meaningful. If this methodical, calm approach to a difficult subject is something you find valuable, a quiet thumbs up or a subscription is a welcome signal. It's a no-pressure way of letting this work find others who might also appreciate a space for slow, deep inquiry. But the most important contribution you can make is simply your continued thoughtful attention. Thank you for being a part of this. Now, let us return to our model. We have examined the waves of light and pressure. We must now turn to the most unique and insidious product of a nuclear explosion, the radiation. To build a robust model, we must fairly consider the counter-arguments and alternative interpretations. In the case of a nuclear detonation, this doesn't mean questioning the fundamental physics, but rather steel-manning the explanations that are often given to downplay or contain the event's consequences. Let's call this the survivable limited event model. The first pillar of this argument is the idea of precision and control. In this view, a modern nuclear weapon is not a blunt instrument of terror, but a tool that could be used in a limited or tactical way. The argument is that a low-yield weapon could be used against a specific military target, like an airfield or a naval base, without causing widespread, indiscriminate destruction to a nearby city. The effects in this model are contained and predictable. The weapon is just another, more powerful form of artillery. The second part of this argument focuses on the resilience of modern infrastructure. It would be argued that the images of Hiroshima, a city made largely of wood and paper houses, are misleading when applied to a modern metropolis. A modern city, with its earthquake-resistant skyscrapers of steel and reinforced concrete, would stand up much better to the blast. The destruction would be less total, and the fires would not spread as easily. The city, in this view, is a harder target. A third pillar of the limited event model concerns civil defense and emergency response. This argument posits that with proper planning, the effects on the population could be mitigated. Duck and cover drills, public fallout shelters, and a well-organized post-strike response by emergency services could save many lives. The event is framed as a manageable disaster, not an apocalypse. It is an extreme event, yes, but one that society can prepare for and recover from, much like a massive earthquake or hurricane. Finally, there is the argument that the long-term effects, particularly from fallout, are often exaggerated. This view would emphasize that radiation levels decay over time, and that with proper sheltering for the first few days or weeks, most people outside the immediate blast zone could avoid a lethal dose. The idea of a permanently uninhabitable radioactive wasteland is dismissed as unscientific fear-mongering. It would be pointed out that Hiroshima and Nagasaki are thriving cities today, proof that a city can recover from a nuclear attack. By putting all these points together, we can construct the Steelman case, a single modern nuclear detonation, if used tactically and if the target city is modern and prepared, would be a horrific and destructive event, but it would be a localized and survivable one. It would not be the end of the world, or even the end of the city. It would be a catastrophe from which recovery is possible. This is the strongest, most coherent argument for a less than apocalyptic outcome. It is essential that we hold this model in mind as we proceed, so that we can compare it to the evidence and see where it holds up and where it begins to break down under the strain of the physics. Now let's present the alternative interpretations, placing them side by side with the survivable limited event model. This is not about declaring one right and the other wrong, but about contrasting the assumptions and identifying the key unknowns that separate the two views. The first contrast is on the nature of the weapon's use. The limited event model assumes a single tactical strike. The alternative interpretation, based on most wargaming scenarios and military doctrines, is that a nuclear exchange is incredibly difficult to control once it begins. The use of a single tactical weapon would likely trigger a retaliatory response, leading to a rapid escalation into a full-scale strategic exchange involving multiple high-yield warheads on many cities. In this view, the single bomb scenario is an unrealistic best case, and the true model should be one of systemic, global collapse. The unknown here is human psychology and decision-making under extreme pressure. Can escalation truly be controlled? The second contrast is on the resilience of a modern city. The limited event model emphasizes the strength of steel and concrete. The alternative interpretation focuses on the city as a complex, interconnected system. While a skyscraper's core might survive the blast, the city is not just its buildings. It is the network of services that connects them: the power grid, the water mains, the communication lines, the transportation network. These systems are far more fragile. The loss of electricity, clean water, and communication would render the surviving structures largely uninhabitable. The city would cease to function, even if parts of it were still standing. The unknown is the true fragility of these interdependent networks when faced with such a massive, simultaneous shock. The third contrast concerns the effectiveness of emergency response. The limited event model assumes an organized response is possible. The alternative view argues that the very conditions of the post-blast environment would make such a response impossible. The destruction of roads and bridges, the presence of intense fires, and the danger of radiation would prevent first responders from even entering the affected area. Furthermore, the responders themselves, the firefighters, doctors, and nurses, along with their equipment and hospitals, would likely be victims of the initial blast, as they are concentrated in the city centre. The assumption of a functioning emergency response system in the aftermath of a nuclear attack on that same system is a critical point of failure in the optimistic model. The unknown is just how completely all organised capacity would be vaporized. Finally, let's contrast the views on long-term recovery. The survivable event model points to Hiroshima and Nagasaki. The alternative interpretation points out that these were unique and in some ways misleading cases. They were single, relatively low-yield bombs dropped on a non-nuclear nation that had already lost the war. The rest of the country was intact and could provide aid. The rest of the world was at peace and could provide support for rebuilding. In a modern strategic exchange, there would be no outside to help. Every major city would be in the same state. The industrial and social capacity to rebuild would be gone. The recovery of two cities in a world at peace is not a valid model for the recovery of civilization after a global nuclear war. By placing these interpretations side by side, we can see that the disagreement is not about the physics of the bomb itself. It is about the assumptions we make about the systems, human, social, and technological, that surround the event. The survivable model assumes these systems are robust and can contain the event. The alternative model assumes they are fragile and will catastrophically fail, amplifying the initial destruction. At this point, we must turn the lens on our own methods. How do we know what we claim to know about the effects of a nuclear explosion? Our knowledge comes from a combination of sources, each with its own strengths and limitations. Our first and most important source is the historical data from the bombings of Hiroshima and Nagasaki. These two events provide our only real-world data on the effects of a nuclear weapon on a city and its population. Scientists and doctors have spent decades studying the damage to the cities, the medical records of the survivors, and the long-term health consequences. This is the bedrock of our understanding. However, this data has limitations. The bombs used were relatively low-yield fission devices. Modern thermonuclear weapons are hundreds of times more powerful and release their energy differently. The cities themselves were constructed differently from modern cities, and the data collection in the chaotic aftermath of a wartime event was inevitably incomplete. Our second source of knowledge is atmospheric testing. From the 1940s to the 1960s, the nuclear powers conducted hundreds of atmospheric tests of nuclear weapons. These tests, often conducted in remote locations like the Pacific Ocean or the Nevada desert, were heavily instrumented. They provided a vast amount of data on the physics of the fireball, the blast wave, and the formation of the mushroom cloud. This is where most of our understanding of the weapon's direct physical effects comes from. The limitation here is that these tests were not conducted on cities. They were conducted on empty landscapes, or on specially constructed test structures. So while they tell us a lot about the weapon, they tell us less about how a complex modern city would respond. Our third source of knowledge is computer modelling. Since the ban on atmospheric testing, scientists have relied on incredibly sophisticated supercomputer simulations to model the performance of nuclear weapons and their effects. These models are based on the fundamental laws of physics and are calibrated using the data from past tests. They allow us to simulate different yields, different types of bursts, and to model the effects on different kinds of structures. The limitation of models is that they are only as good as the assumptions and data that go into them. Modeling the full complexity of a city, with its millions of individual components and interconnected systems, is an immense challenge. The models are very good at predicting the physical effects like overpressure, but less certain at predicting the complex cascading systemic failures that would follow. Finally, we have data from large-scale conventional explosions and disasters. The study of massive industrial accidents, large-scale fires, and the effects of conventional bombing campaigns in wartime can give us insights into how urban environments burn and how infrastructure fails. By combining all of these sources, the human-scale data from Japan, the physics data from testing, the predictive power of computer models, and the analog data from other disasters, we can build a reasonably confident picture. But we must always be aware of the detection limits and the survivorship bias in our data. We only know what we were able to measure. With this renewed understanding of our methodology, let's reopen the main thread and turn to the most unique and unnerving aspect of a nuclear detonation: the radiation. The language we use to discuss nuclear weapons is often laden with euphemisms and abstractions that can obscure the physical reality. It is a vocabulary that has been carefully constructed over decades to make the unthinkable seem manageable. A conscious examination of this framing is necessary for a clear understanding. Consider the term device or physics package instead of bomb or weapon. These are terms from the world of engineering. They are neutral, technical, and stripped of intent. A device is something you test. A weapon is something you use on people. The language helps to create a psychological distance from the consequences. The yield of a weapon is measured in kilotons or megatons. This is an abstraction. It compares the nuclear explosion to a chemical one, that of TNT. While it gives a sense of scale, it masks the fundamental differences. A 1 megaton bomb is not just 1 million tons of TNT, it also releases a wave of nuclear radiation and a thermal pulse of stellar intensity, effects that TNT does not produce. The equivalence is only in the blast energy, and even that is a simplification. The targets of nuclear weapons are often referred to in sterile, strategic language. A city becomes a counter-value target. Human beings become collateral damage. The goal of this language is to sanitize the reality. It transforms a city full of homes, schools, and hospitals into a strategic calculation on a map. It is the language of systems analysis applied to mass destruction, and in doing so, it erases the human dimension. Even the central doctrine of the Cold War, mutual assured destruction, with its almost playful acronym MAD, is a kind of linguistic trap. It presents the situation as a stable, logical, almost game-like equilibrium. It frames the possession of thousands of world-ending weapons as a rational strategy for maintaining peace. It obscures the immense risk, the possibility of accident or miscalculation, and the profound ethical questions that this posture entails. When we use a metaphor for the blast, like a storm, we must be careful of its limits. A storm is a natural phenomenon. It is powerful and destructive, but it is not malicious. It has no author. A nuclear detonation is not a natural phenomenon. It is a man-made storm. It is the product of deliberate human choices, engineering, and strategic planning. To frame it as a natural disaster is to absolve it of its human origins. Our goal in this exploration is to gently pull back this curtain of abstract and euphemistic language. By focusing on the concrete physics of the event, the overpressure in psi, the thermal energy in calories per square centimeter, the radiation dose in sieverts, We are attempting to ground the conversation in physical reality. This is not to be sensationalist, it is the opposite, it is to be precise. By understanding the mechanisms clearly, we are better able to see through the linguistic frames that have been constructed around this technology. It allows us to have a more honest and clear-eyed conversation about what these weapons are and what they do. Let's apply this disciplined, physics-based approach to a concrete scenario. We will walk through the effects of our 300 kiloton airburst on a typical residential building, a 2-story wood frame house located 5 kilometers, 3 miles from ground zero. This is the application of our evidence track I, thermal, and 2, blast, together. Time, 0 seconds, the detonation occurs. Time, 0.00001 seconds. The first thermal pulse arrives, travelling at the speed of light. It is mostly ultraviolet light. For the house, this has little effect, other than perhaps causing some surface plastics to degrade slightly. Time, 0.1 to 10 seconds. The main second thermal pulse radiates from the fireball. The house has a direct line of sight. The side of the house facing the explosion absorbs an immense amount of thermal energy. The paint on the wooden siding blisters, chars, and then bursts into flame. The asphalt shingles on the roof ignite. The curtains inside the windows, if they are dark-coloured, spontaneously combust. The dry wooden deck in the backyard begins to smoulder and then burn. In the space of about 10 seconds, the house is on fire in multiple independent locations. Time, 15 seconds. The blast wave arrives. It has been travelling at the speed of sound and is now at our 5-kilometre mark. The overpressure is approximately 5 psi. The front of the shock wave hits the house. The windows, which may have already cracked from the thermal stress, are instantly shattered and blown inwards. The shock wave then engulfs the house. The 5 psi overpressure exerts a force of over 36,000 kilograms, 80,000 pounds, on the side of the house. The wooden structure is not designed for this. The nails pull out, the beams splinter, and the walls are pushed in. The roof is lifted up and torn apart by the pressure differential. A fraction of a second later, the dynamic pressure, the powerful wind, arrives. This wind, travelling at over 250 kilometers per hour, 160 miles per hour, catches the now weakened structure. It picks up the debris from the collapsed walls and roof and hurls it inwards. The house is not just crushed, it is violently dismantled and scattered. The chain of causality is clear. The light sets the house on fire. The pressure wave demolishes it. The result is not a standing, burning house. It is a pile of burning, splintered rubble. The fires, which were separate moments ago, now merge into a single large fire, fed by the exposed wood and fanned by the lingering winds of the blast. This is the fate of a single house. Now, multiply this by the tens of thousands of similar houses in the concentric ring between 4 and 6 kilometers from ground zero. The entire suburban landscape is simultaneously set on fire and reduced to rubble. This is how the destruction of the city's physical structure happens, house by house, street by street, in a matter of seconds. Now, let's contrast this with a different type of structure, applying our second evidence track, systems and feedbacks to a larger scale. We'll examine the effects on a modern steel-frame skyscraper located 2 kilometers, 1.2 miles from ground zero. Here, the overpressure from our 300 kiloton airburst is much higher, around 15 pounds per square inch. The dynamic pressure winds are over 500 kilometers per hour, 300 miles per hour. Time, 6 seconds. The blast wave arrives. The facade of the building is made of glass and aluminum panels, a curtain wall. This is not a structural part of the building. The 15 psi overpressure instantly destroys it. The entire glass skin of the building on the side facing the blast is shattered and torn away. The powerful winds then enter the building, gutting the office floors, sweeping furniture, computers, and interior walls into a destructive vortex. The building's core, however, is a massive structure of reinforced concrete and heavy steel beams. It is designed to withstand strong winds and earthquakes. Will it survive? It is likely that the core structure would remain standing, at least initially. It would be a gutted, skeletal wreck, but it would not be completely leveled like the wooden house. This is where the systems and feedback effects come in. The building may be standing, but it is no longer a functioning system. The electricity is gone, the water and sewer lines are severed, the elevators are inoperable. It is a dead hulk. But the real feedback loop comes from the fires. The thermal pulse would have ignited fires on the office floors through the shattered windows. The blast wave would have ruptured natural gas lines within the building. The result is a high-rise building with multiple intense fires burning on many floors simultaneously, fueled by gas leaks. A modern skyscraper's fire suppression system, sprinklers and alarms, depends on water pressure and electricity. Both of these are gone. There is no fire department to respond. It has also been destroyed. The fires in the skyscraper will burn unchecked. This is where the building's own structure can turn against it. While steel does not burn, it loses its structural integrity at high temperatures. In a sufficiently hot, prolonged fire, the steel beams can soften, bend, and collapse. The collapse of one floor can then trigger a pancaking collapse of the floors below it. So, while the skyscraper might survive the initial blast that the wooden house did not, it is critically vulnerable to the secondary effect of fire. The system, once its protective feedbacks, fire suppression, are removed, is now highly unstable. The scale shift from a small wooden house to a massive steel skyscraper does not necessarily mean greater safety. It just means a different, slower, but potentially just as total mode of failure. The house is destroyed by pressure. The skyscraper is destroyed by fire. The end result is the same, a non-functional ruined structure. We have spoken of the waves of light and pressure. Now we must turn to the third and most unique product of a nuclear explosion, an effect that is both invisible and enduring, the nuclear radiation. This is our evidence track 3, and we'll approach it by using the archetype of a poisoned environment. This is not a poison in the chemical sense. It is a poison of energy. A nuclear explosion releases immense quantities of high-energy particles and rays, neutrons and gamma rays, that can penetrate matter and damage living cells. This radiation is delivered in 2 distinct waves. The first wave is the prompt radiation. This is an intense burst of gamma rays and neutrons that are emitted from the fireball in the first minute following the detonation. They travel outwards at or near the speed of light. This radiation is incredibly intense but has a limited range, as it is absorbed by the air. For our 300 kiloton airburst, the lethal range of prompt radiation is about 3 kilometers, nearly 2 miles from ground zero. Anyone within this radius, who is not shielded by many feet of concrete or earth, would receive a fatal dose of radiation in a matter of seconds. However, within this range, the effects of the blast and heat are so extreme that they are the primary cause of death. The prompt radiation is, in a grim sense, redundant for anyone close to the center of the explosion. The second wave of radiation is the one that has longer-term consequences. This is the residual radiation, most commonly known as fallout. The mechanism is this. The explosion itself creates a host of new, highly radioactive atomic nuclei, the fission products. The intense heat of the fireball vaporizes everything within it, including the weapon itself, and tons of dirt and debris from the ground that are sucked up into the rising mushroom cloud. In the mushroom cloud, the radioactive fission products condense onto these dirt and dust particles. As the cloud cools and is carried by the wind, these radioactive particles begin to fall back to the ground. This is fallout. It is, in effect, a rain of radioactive dust. The area affected by fallout is determined by the wind. The fallout creates a plume-shaped pattern of contamination downwind from the detonation site. This plume can extend for hundreds of kilometers. The heaviest, most radioactive particles will fall out close to the detonation site within the first hour. Lighter particles will travel much farther and fall out over a period of hours or days. The fallout emits radiation, primarily gamma rays, which can penetrate buildings. The danger from fallout is highest in the first few hours and days after the explosion. The radioactivity decays over time, quite rapidly at first, then more slowly. A general rule of thumb is that for every 7-fold increase in time, the radiation level decreases by a factor of 10. The implication is the creation of a vast, invisible landscape of poison. The ground itself becomes dangerous. Anyone in the fallout plume without adequate shelter would be exposed to a continuous dose of radiation. A lethal dose could be accumulated in a matter of hours in the areas of heavy fallout, and a sickness-inducing dose over a wider area. The city and the surrounding countryside are rendered uninhabitable, not by destruction, but by an invisible, energetic poison. The long-term consequences of this radiation exposure for survivors are a separate and complex issue. But the immediate effect is to create a deadly zone of denial that can be far larger than the zone of blast and fire, making any attempt at rescue or recovery a lethal proposition. The creation of this vast, poisoned landscape has profound consequences for the planet and for the biosphere. Let's translate the abstract concept of radiation dose into its tangible effects on living systems. This is about the long-term habitability of the contaminated area. For human beings, the primary consequence of fallout is the risk of acute radiation sickness from external exposure to gamma rays. This is a direct, dose-dependent illness. The radiation damages the cells in the body, particularly rapidly dividing cells like those in the bone marrow and the lining of the digestive tract. The higher the dose, the more severe the sickness and the lower the chance of survival. This makes the contaminated area a no-go zone for unprotected people for a period of weeks to months, depending on the intensity of the fallout. But the danger is not just external. The radioactive particles can be ingested or inhaled. They can settle on crops, be absorbed by plants, and enter the food chain. They can contaminate water supplies. This internal contamination brings the source of the radiation inside the body, where it can do long-term damage, leading to cancers and genetic mutations. The effects are not limited to humans. All complex life is vulnerable to radiation. Mammals are particularly sensitive. Trees, especially conifers, are also highly susceptible to radiation damage. The fallout plume would be a zone of death for forests and wildlife. Insects are generally more resistant, and microbes even more so. The effect would be a radical and grotesque simplification of the ecosystem. The complex web of life would collapse, leaving a landscape dominated by the most radiation-resistant lower organisms. The planet itself, the geology, is largely immune, but the topsoil would become a reservoir of long-lived radioactive isotopes like cesium-137 and strontium-90. These isotopes have half-lives of about 30 years. This means they remain dangerously radioactive for decades and can be incorporated into the ecosystem for centuries. They would be taken up by the grasses that eventually regrow, eaten by the insects and rodents that survive, and passed up the newly forming, impoverished food chain. The area does not remain a sterile wasteland forever. Life is resilient. Over time, as the radiation levels decay, pioneer species will begin to recolonize. But the ecosystem that returns will be different. The shadow of the contamination will linger for generations, in the form of increased cancer rates in animal populations and elevated genetic mutation rates. The experience of Chernobyl provides a real-world, if imperfect, analogue. The 30-kilometre exclusion zone around the reactor, though now teeming with wildlife in the absence of humans, is still a laboratory for studying the long-term effects of chronic radiation exposure on an ecosystem. The implication of our fallout model is the creation of a long-term ecological wound. The city is not only physically destroyed but also rendered biologically toxic for a significant period. The recovery of the natural environment is a process that operates on the timescale of decades and centuries, a slow, patient healing of a poisoned land. We now have all the primary physical effects on the table: the thermal pulse, the blast wave, and the radiation from fallout. Our next evidence track is not about a new physical phenomenon, but about the synergistic collapse of the city as a system. This is the story of how the physical damage translates into a complete breakdown of the urban organism. Think of a modern city as a living entity. It has a metabolism. It consumes energy, water, and food, and it produces waste. It has a circulatory system, the transportation network of roads, rails, and subways. It has a nervous system, the communication network of fiber optic cables, cell towers, and data centers. All of these systems are interconnected and interdependent. The nuclear detonation is a simultaneous, catastrophic shock to all of these systems at once. Let's trace the archival record of this systemic failure, as seen in the physical destruction. The power grid is the first to fail. The blast wave would destroy power plants, substations, and transmission lines within its radius. But there is another, more subtle effect: the electromagnetic pulse, or EMP. A high-altitude nuclear explosion generates an intense, instantaneous pulse of electromagnetic energy that can damage or destroy unprotected electronic equipment over a vast area. For our lower-altitude airburst, the local EMP effect would still be significant. It would fry the electronics that control the power grid, causing a near-instantaneous citywide blackout. The city's metabolism stops. The water system fails next. The destruction of pumping stations and the severing of water mains by the blast means the system loses pressure. Clean water stops flowing to homes and, crucially, to fire hydrants. The city loses its ability to fight the thousands of fires that have just been started. The lack of water also creates a massive public health crisis for any survivors. The communication system is obliterated. Cell towers are destroyed. Fiber optic cables are cut. The internet, landlines, and emergency radio systems all cease to function. The city's nervous system is severed. There is no way to coordinate a response, no way to call for help, no way to know what is happening in the next neighborhood over. The survivors are isolated in a sea of destruction. The transportation system is annihilated. Roads are blocked by mountains of debris from collapsed buildings. Bridges and overpasses are destroyed. The subway system, if the city has one, is flooded or collapsed. There is no way in or out of the city's core. The record of this collapse is written in the rubble, the tangled power lines, the broken water mains, the impassable streets. These are the artifacts of a systemic failure. The key insight here is the concept of cascading failure. The failure of the power grid contributes to the failure of the water system. The failure of the transportation system prevents the repair of any other system. Each failure reinforces the others. The implication is that the city does not just die, it disintegrates. The complex, interconnected organism that was a thriving metropolis is reduced, in a matter of minutes, to a collection of isolated, non-functional ruins. It is a state change from which there is no easy recovery. The very systems that would be needed to manage the crisis and begin the process of rebuilding are the first casualties of the event. The constraints on our knowledge of this systemic collapse are significant. We can model the failure of individual components with some confidence, but predicting the precise way in which these failures would cascade through a specific, unique city is incredibly difficult. Every city is a different kind of system, with its own unique vulnerabilities and interdependencies. We can infer with high confidence that a city-wide, long-term blackout would occur. The destruction of the electrical grid's physical infrastructure within the blast radius is a certainty. The added effect of EMP makes the failure even more assured. We can also be confident that the water and communication systems would suffer catastrophic failure for similar reasons. The physical destruction of their core components is unavoidable. Where our confidence becomes lower is in the modelling of the human response to this collapse. In the absence of all modern services, how would the survivors behave? How would they organise? How would they find food and water? We have some data from large-scale natural disasters, like Hurricane Katrina, which show how quickly social order can break down when critical infrastructure fails. But even these analogues are imperfect. A natural disaster is typically localised, and help eventually arrives from the outside world. In our scenario, the destruction is far more total, and the possibility of outside help is severely limited. We simply cannot know for certain how a population would respond to a crisis of this magnitude. Our models of human behaviour under such extreme stress are largely speculative. Another constraint comes from the uniqueness of modern systems. Much of our critical infrastructure is now controlled by complex computer-based systems known as SCADA systems. The vulnerability of these systems to EMP is a subject of intense debate. A widespread failure of these control systems could have unpredictable, cascading effects that are not yet fully understood. We lack real-world test data for this kind of event on our modern, digitized infrastructure. So, we must place confidence bands around our conclusions. We can be certain of the physical destruction of the city's primary infrastructure systems. We can be certain that this would lead to a complete breakdown of all normal urban services for a prolonged period. What we cannot be certain of is the detailed, minute-by-minute unfolding of this systemic collapse, or the precise nature of the human social response in its aftermath. The archival signals from Hiroshima and Nagasaki give us some clues, but they are from a different era, with a different technology and a different kind of society. The story of the systemic collapse of a modern, digitized metropolis remains, thankfully, in the realm of theory and model, and we must acknowledge the inherent uncertainties in that modelling process. We have reached the midpoint of our solemn exploration. We have traced the initial waves of energy, light, pressure, and prompt radiation, and we have seen how they combine to create a perfect storm of destruction. We have examined the city not just as a collection of buildings, but as a complex interconnected system, and we have modelled its catastrophic, cascading failure. We have also looked at the longer-term threat of fallout, the invisible poison that renders the landscape uninhabitable. Before we move into the second half of our inquiry, let's just pause and flag what is to come. We will now begin to synthesize these effects, looking at the overarching environmental consequences, such as the potential for climate change in the form of nuclear winter. We will also turn our attention to the human scale of the aftermath, exploring the medical crisis that would unfold and the immense challenges of survival. This coming synthesis will require us to hold all the threads we've gathered so far in our minds at once: the fires, the rubble, the radiation, and the systemic collapse. We are moving from describing the individual blows of the weapon to understanding the total integrated state of the post-nuclear environment. The goal remains the same: calm, methodical understanding. For now, let the ideas we've discussed settle. The synthesis is yet to come. Let's now zoom out from the single city and consider the conversation between this event and the global atmosphere. If our thought experiment were expanded from a single detonation to a large-scale nuclear exchange, what would be the consequences for the planet's climate? This is our Evidence Track 5, which explores the concept of nuclear winter. The mechanism begins with the fires. As we've seen, a nuclear explosion over a city is incredibly effective at igniting a massive firestorm. The intense heat of these firestorms would burn not just wood and vegetation, but also plastics, asphalt, and other petroleum-based materials, creating vast plumes of thick, black, sooty smoke. The crucial element here is the powerful updraft of the firestorm. It acts like a giant chimney, lifting this black smoke high into the atmosphere, potentially punching it up into the stratosphere. The stratosphere is the stable layer of the atmosphere above the weather. Once particles get into the stratosphere, they are not easily rained out. They can persist there for months or even years. The hypothesis of nuclear winter, first developed by atmospheric scientists in the 1980s, is this: a large-scale nuclear war between major powers, targeting dozens or hundreds of cities, would inject a massive amount of this black soot into the stratosphere. This soot is very good at absorbing sunlight. A stratospheric soot layer would act like a shield, blocking a significant portion of incoming sunlight from reaching the Earth's surface. The consequence would be a rapid and dramatic drop in global temperatures. The models from the 1980s predicted a cooling of as much as 20 to 30 degrees Celsius in the interior of continents, plunging the planet into a deep artificial winter that could last for years. This depersonified conversation between the burning cities and the atmosphere is a powerful feedback loop. The initial event on the ground creates a secondary effect in the atmosphere that then feeds back to fundamentally alter the climate on the ground. More recent studies, using modern, sophisticated climate models, have refined these predictions. The predicted cooling is generally less extreme than in the original studies, but still catastrophic. Even a limited regional nuclear exchange, for example between India and Pakistan, involving 100 Hiroshima-sized bombs dropped on cities, is now modelled to inject enough soot into the stratosphere to cause a global average cooling of 1 to 2 degrees Celsius. This may not sound like much, but it would be a greater climate change than anything experienced in recorded human history. It would be enough to cause widespread crop failures and global famine. A full-scale exchange between the US and Russia would cause much more severe cooling for a longer period. The nuclear winter hypothesis is a powerful example of an indirect systemic effect. The danger is not just the immediate blast and radiation, but the potential for the event to trigger a global, self-inflicted climate catastrophe that would affect everyone on the planet, regardless of where the bombs fell. The resilience of the global climate system is immense, but it is not infinite. It has thresholds. The nuclear winter hypothesis explores what happens when one of those thresholds is crossed by the injection of a massive, unnatural atmospheric pollutant. The failure mode here is a chilling one. The planet's primary energy source, the sun, is effectively turned down. The entire global ecosystem, which is based on photosynthesis, would be starved of its fundamental fuel. The initial models of nuclear winter in the 1980s were a subject of intense scientific and political debate. They were based on simplified, one-dimensional climate models and had significant uncertainties. Let's examine the resilience of this hypothesis and the failure modes of the models themselves. The primary threshold for igniting a nuclear winter is the amount of soot injected into the stratosphere. If the amount is too small, or if the smoke does not get lifted high enough, it will be washed out of the lower atmosphere by rain in a matter of weeks, and no significant long-term climate effect will occur. The key question then is how much smoke a burning city produces and how high it goes. This is a major source of uncertainty. We have never observed a nuclear firestorm. The data from conventional firestorms like Hamburg and from large-scale forest fires can give us clues, but they are imperfect analogues. The failure modes of the early models were that they might have overestimated the amount of fuel in cities, or the efficiency with which that fuel would be converted to black, sooty smoke. They may not have perfectly modelled the complex microphysics of how soot particles clump together and fall out of the atmosphere. However, the resilience of the core idea has been demonstrated by the fact that every new generation of more sophisticated climate models has reaffirmed the basic conclusion. Modern, three-dimensional global circulation models, the same ones used to predict the effects of global warming, have been applied to the problem. They consistently show that a significant injection of stratospheric soot leads to a significant and prolonged global cooling, along with other effects, like a dramatic reduction in global rainfall and a massive loss of the protective ozone layer. The core physics is robust. If you put a lot of black stuff in the sky, it will get dark and cold on the ground. The implications of this potential systemic failure are profound. It means that the consequences of a nuclear war are not just local or regional, they are global. A nuclear exchange between two countries could trigger a worldwide famine that kills billions of people who had nothing to do with the original conflict. This transforms our understanding of what is at stake. It is not just about the destruction of cities, it is about the potential to trigger a global environmental catastrophe that could threaten the survival of human civilization itself. The system is so interconnected that a failure in one part, a regional conflict, can cascade to cause a failure of the whole planetary life support system. The nuclear winter concept represents the ultimate planetary-scale feedback loop from a human-created event. To make the systemic nature of this event clearer, let's use our analogy of the city as a biological operating system, but this time with a crucial caveat. We will look at biology as a kind of code, a set of instructions for building and maintaining a complex system. In this analogy, the DNA of an organism is its source code. It contains the instructions for building every protein, every cell, every organ. The city too has a kind of code. It is not genetic, but it is informational. It is in the blueprints of its buildings, the schematics of its power grid, the zoning laws that govern its growth, and the collective knowledge stored in its libraries, data centers, and the minds of its citizens. This is the city's informational DNA. A nuclear detonation is an act of catastrophic information destruction. It is not just the destruction of the physical hardware, the buildings and the infrastructure. It is the erasure of the software, the code that makes the city work. The blast wave that destroys a library or a university is erasing centuries of accumulated knowledge. The EMP that fries the servers in a data center is deleting the city's financial records, its administrative data, its digital memory. The death of the city's skilled engineers, doctors, and administrators is the erasure of the wetware, the human knowledge required to run and repair the city's complex systems. This is a key implication of the systemic collapse. A city is more than its physical parts. It is the information that organizes those parts into a functioning whole. When that information is lost, the city cannot be simply rebuilt. It has lost its blueprint. Now, for the crucial caveat. Biological code, DNA, has a property that a city's informational code does not. It is self-replicating and it is distributed. Every cell in your body, with a few exceptions, contains a complete copy of your genetic blueprint. This massive redundancy is what makes life so resilient. Even if many cells are destroyed, the information is preserved in the survivors, and the organism can heal and regrow. A city's informational code is not like this. It is centralized and fragile. The blueprints for the water system are in one building. The financial records are in a few data centers. The skilled knowledge is in a small percentage of the population. There is no city-wide redundant backup of the total system information. This is a fundamental difference in resilience framing. Life's resilience comes from its distributed, redundant information storage. A city's fragility comes from its centralized, brittle information storage. After a nuclear attack, the survivors would not just be faced with a ruined physical landscape, they would be faced with a profound information vacuum. How do you restart a power grid without the schematics and the trained engineers? How do you purify water without the knowledge of how the system works? This analogy helps us understand the true depth of the destruction. It is an informational apocalypse as much as a physical one. It explains why the recovery is not just a matter of clearing rubble and laying new bricks. It is a matter of rediscovering the knowledge of how to make a city work. This is a task that could take generations. The resilience of biological systems, honed over billions of years, is based on a fundamentally different information architecture than the one we have used to build our own complex societies. The nuclear event brutally exposes the fragility of our centralized model. The destruction of the city's informational DNA has profound implications for the nature of the post-attack world. It would be a world not just physically ruined, but intellectually impoverished. This leads to a reframing of what recovery and resilience even mean in this context. A system that has lost its core operating instructions cannot simply be rebooted. It has to be reinvented from the ground up, using whatever fragmented knowledge and surviving components remain. The recovery would not be a process of rebuilding the old world, it would be a process of building a new, much simpler world on the ruins of the old one. The survivors would be thrown back into a pre-industrial state, but without the skills and knowledge that people in pre-industrial times possessed. They would be surrounded by the tantalizing but unusable relics of a high-tech civilization. A car is useless without fuel. A hospital is useless without electricity and trained doctors. A computer is useless without a network and a power source. The system's failure would be graceful in the sense that it wouldn't just vanish, it would degrade to a much lower state of complexity. But the transition would be anything but graceful for its inhabitants. This highlights the difference between robustness and perfection. Our modern technological civilization is, in many ways, a system optimized for performance and efficiency, not for robustness against this kind of catastrophic shock. It is a high-performance racing engine, not a durable tractor engine. Its very complexity and interdependence are its greatest vulnerabilities. The resilience in this scenario would have to come from the human level. It would be in the small groups of survivors, rediscovering old technologies, adapting to the new environment, and slowly, over generations, rebuilding a new kind of society. The resilience would not be in the technology, but in the human spirit. But the task would be monumental. The loss of specialized knowledge would be a critical barrier. How many people in a modern city know how to grow their own food, purify water, or forge metal from raw ore? Our civilization is built on an extreme degree of specialization, and a nuclear event would shatter the network that makes that specialization possible. The adaptive systems that would emerge would not be flawless. They would be cobbled together, good enough solutions for survival in a broken world. The long, slow process of recovery would be a climb back up the ladder of complexity, a process that could take centuries or even millennia. The informational collapse is, in many ways, a deeper and more enduring wound than the physical destruction. The rubble can be cleared, but the lost knowledge is much harder to recover. To truly understand the alien nature of the post-nuclear world, let's try to reconstruct the sensory experience of standing in the ruins of our city a few days after the detonation. This is our deep time panorama, a journey to an unfamiliar world that is not distant in time, but has been created in our own time. The first thing you notice is the light. The sun is a pale, dim disk in a sky that is permanently grey or a sickly brownish yellow. The thick clouds of smoke from the smouldering ruins of the city and from distant burning forests block most of the sunlight. It is a world of perpetual twilight, even at midday. The air is cold, unnaturally so, a direct consequence of this new artificial cloud cover. The second thing you notice is the silence. The normal sounds of the city, the hum of traffic, the distant sirens, the voices of people are gone. The silence is profound, absolute. It is broken only by the mournful sound of the wind moving through the skeletal remains of buildings. There are no birds, there are no insects. It is the silence of a dead or dying ecosystem. The third thing is the smell. The air is thick with the acrid smell of smoke, of burnt plastic, of decay. It is a chemical, industrial smell, the smell of a civilization being consumed by fire and rot. Now, look at the landscape. The familiar grid of streets is gone, replaced by a chaotic three-dimensional maze of rubble. Mountains of twisted steel, shattered concrete, and blackened debris cover everything. Travel is not a matter of walking down a street, but of climbing over treacherous, unstable piles of wreckage. The landmarks that once defined your mental map of the city are gone. You are in a place that is simultaneously familiar and utterly alien. You are disoriented in your own home. The colours of this world are muted, monotonous. Everything is coated in a layer of fine grey radioactive dust. The world is a monochrome of black, grey and brown. There is no green. The plants and trees are dead, either incinerated by the firestorm or killed by the radiation. Water is a source of constant danger. The rivers are choked with debris and contaminated with industrial chemicals, human waste and radioactive fallout. Puddles of rainwater are not a source of life, but a source of invisible poison. This is a world that has been fundamentally altered at the chemical and physical level. It is a hostile environment, actively working against survival. The very ground you walk on, the air you breathe, the water you might be tempted to drink, all are contaminated. Rebuilding this sensory world is crucial because it takes the abstract concepts of destruction and fallout and turns them into a tangible, lived reality. It underscores the totality of the transformation. This is not just a damaged city. This is a new kind of planetary surface, a toxic and alien landscape created in an instant by a human technology. The survivors would not be rebuilding their old world. They would be pioneers, strangers in a strange land that was once their home. The creation of this new, hostile landscape has profound consequences for any chance of recovery. It is a world where the most basic requirements for human life, clean air, clean water, safe food and shelter, have been systematically removed. The moisture transport limits are now not about climate, but about access. Even if there are sources of clean water a few dozen kilometers away, the destruction of all forms of transportation and the dangerous, impassable landscape of rubble make it almost impossible to reach. The harsh interiors we must now consider are not those of a continent, but of the ruined city itself. The city, once a concentration of resources, has become a concentration of hazards. The very density that made it efficient now makes it a death trap. The rubble makes travel impossible. The decaying organic matter is a breeding ground for disease. The remnants of industrial sites have released a toxic chemical soup into the environment. The normal biome of the city, the parks, the gardens, the trees that line the streets, is gone. It has been replaced by a new radiological biome. The rules of this ecosystem are governed by the half-lives of isotopes and the varying radiation tolerances of different species. The survivors are not the most complex or the most intelligent, but the most robust. Rats, cockroaches, certain types of weeds. A new, simplified and grotesque food web would begin to form on the ruins. The climate of the city has also changed. The urban heat island effect is gone, replaced by the chilling shadow of the smoke pool. The local weather patterns are disrupted. This is a world where every single one of the systems that support human life has been simultaneously and catastrophically broken. There is no power. There is no sanitation. There is no communication. There is no organized food production. There is no healthcare. Each of these failures would be a major disaster on its own. The fact that they all happen at once and are overlaid with the persistent threat of radiation creates a survival challenge of an almost unimaginable scale. The consequences of this new supercontinent of rubble are a near total breakdown of social organization. The survivors would be atomized, thrown back onto their own immediate resources in an environment that is actively hostile to them. The delicate, complex web of trust and cooperation that makes a society function would be shattered. The long, slow process of recovery would have to start from the most basic level, securing a source of uncontaminated water, finding a safe place to shelter, and scavenging for non-perishable food, all while navigating a lethal and unfamiliar landscape. The harsh reality of the New World is that the city, humanity's greatest invention, has been turned into its most effective tomb. Even a model as grim and well-supported as this one must be subjected to the most rigorous criticism. Let's step back into the skeptic's corner and outline the strongest arguments against this total collapse scenario and identify the potential falsifiers that could challenge it. The strongest criticism revolves around the nuclear winter hypothesis. While the basic physics is sound, the magnitude of the effect is highly dependent on a series of uncertain variables. How much fuel is actually in a modern city? How much of it would actually burn in a firestorm? How much of that would be converted to the kind of black, sunlight-absorbing soot that is needed? And how efficiently would that soot be lifted into the stratosphere? A skeptic would argue that these numbers are overestimated. They would point out that modern cities have more non-combustible materials, and that the smoke from a fire might not be as black or rise as high as the models predict. A potential falsifier for the most extreme nuclear winter scenarios would be a detailed, modern analysis of urban fuel loads and fire dynamics that conclusively shows that a city-wide firestorm is unlikely, or that it would not produce enough soot to cause a major climate effect. Another major line of criticism targets the assumptions about the complete and permanent collapse of social order. Humanity, the argument goes, is incredibly resilient and adaptable. Even in the face of the most extreme disasters, people organize, cooperate, and help each other. The idea of a total descent into a Mad Max-style anarchy is a cinematic trope, not a sociological certainty. A skeptic would argue that surviving communities would form, that knowledge would be preserved, and that the process of rebuilding, while incredibly difficult, would begin almost immediately. A potential falsifier for the total social collapse model would be detailed historical or sociological studies of other extreme disasters that show a consistent pattern of rapid, spontaneous reorganization and high levels of pro-social behavior, even in the absence of central authority. A third criticism focuses on the long-term effects of radiation. The skeptic would argue that the dangers of low-level radiation are often exaggerated, and that the natural world's ability to recover from radiological contamination is underestimated. They would point again to Chernobyl, where wildlife is thriving despite the persistent radiation. They would argue that while the initial fallout period is incredibly dangerous, the long-term habitability of the region would be restored faster than the models suggest. A falsifier here would be long-term ecological studies from Chernobyl or other contaminated sites that show persistent, severe, multi-generational damage to ecosystem health and genetic integrity, proving that the recovery is not as robust as it appears on the surface. We must concede where our model is most speculative. The precise nature of the global, systemic, cascading failure of our interconnected modern world, our financial systems, our digital infrastructure, our global supply chains, in the face of a large-scale nuclear exchange is simply unknowable. We can model the physical effects, but the behavior of these complex human systems under such stress is in the realm of deep uncertainty. By engaging with these criticisms, we make our model stronger. It forces us to acknowledge our assumptions and to be honest about the error bars around our predictions. The scientific process is a constant dialogue between theory and skepticism. The synthesis we have built is the current best fit for the available evidence, but it must always remain open to challenge, revision, and falsification. Our investigation of this event is an exercise in forensic science on a planetary scale. The mindset required is that of a detective working with incomplete, degraded, and often ambiguous evidence. We must be constantly aware of the layers of bias and erasure that separate us from the event itself. Our priors, our pre-existing mental models, are powerful but dangerous. We are biased by our own experience of a world with a stable climate and functioning infrastructure. It is difficult for us to truly imagine the reality of a systemic collapse because it is so far outside our lived experience. We are also biased by the fictional depictions of nuclear war in movies and books, which are almost always designed for dramatic effect not scientific accuracy. We must constantly work to set aside these priors and look at the evidence with fresh eyes. Anomalies are our most valuable clues. When the data from Hiroshima did not perfectly match the predictions of the early models, it was an anomaly. This forced scientists to refine their understanding of how the blast wave interacts with a complex urban landscape. The anomalous survival of certain structures close to ground zero taught them about the importance of shielding and reinforcement. A detective cherishes the clue that doesn't fit, because it is the clue that points to a deeper, more complex truth. And we must always contend with erasure. Our most detailed data comes from the two historical uses of these weapons, but a real-world test of a modern thermonuclear weapon on a modern city has thankfully never been performed. The data simply does not exist. We are forced to extrapolate from lower-yield events, from atmospheric tests on empty landscapes, and from computer models. The most important parts of the archive are missing. This detective mindset frees us from the need for absolute certainty. It allows us to build a plausible reconstruction, a theory of the case, that is consistent with all the available lines of evidence. It allows us to say, given what we know, this is the most likely sequence of events. With this renewed awareness of our methodological humility, we can now reopen the main thread. We have built a detailed picture of the physical destruction and the systemic collapse of a single city. We have considered the potential for a global climate catastrophe. We are now prepared to move towards our final synthesis, to bring these threads together and to contemplate the meaning of this knowledge for ourselves, living in this world, now. Let's once again bring the entire system back to the scale of the human body, in this room. We have journeyed through an abstract model of destruction. Now, let's ground it in our own physical reality. Take a breath. The process of respiration, of your body taking in oxygen and using it to generate energy, is a delicate and complex one. It relies on the air having a specific composition, a specific pressure. The medical aftermath of a nuclear detonation is a story of how the fundamental systems of the human body are overwhelmed by an environment that has become hostile to them. The burns from the thermal pulse, the trauma from the blast wave, the cellular damage from the radiation, these are not separate injuries. For a survivor, they would be a synergistic combination of insults to a single, delicate biological system. A person with severe burns also has internal injuries from the blast and a compromised immune system from the radiation. The body's ability to heal is overwhelmed. This is the embodied reality of the systemic collapse we discussed at the city scale. The city's infrastructure fails because its components are hit by multiple, simultaneous stresses. The human body fails for the same reason. This perspective gives us an agency that is not about prescriptive action, but about appreciation. It is an invitation to appreciate the quiet, constant, and miraculous work that your body is doing right now to maintain its own internal stability, its homeostasis. It is an invitation to appreciate the stability of the external environment that allows your body to do this work so effortlessly. We are exquisitely adapted to this world. The Permian extinction taught us that when the world changes too fast, that adaptation becomes a liability. The nuclear event is a human-created version of the same fundamental lesson. By bringing the story back to our own breath, our own bodies, we are not trying to induce fear. We are trying to foster a deeper, more visceral understanding of the preciousness and the contingency of our own existence. We are the descendants of a lineage of life that survived planetary catastrophes. We are the beneficiaries of a global civilization that has, so far, managed to hold this self-destructive power in check. To feel your own aliveness here and now in a stable and life-supporting world is the most powerful and personal counterpoint to the abstract horror of the model we have been exploring. Let's introduce one final evidence track before our synthesis, the energy budget of the weapon itself. By understanding the sheer magnitude of the energy flows, we can grasp the fundamental physics that drives all the other effects. A nuclear weapon is, at its core, a device for the instantaneous conversion of matter into energy. Our 300 kiloton device releases the same amount of energy as 300,000 tons of TNT. This is an energy release of approximately 1.25 quadrillion joules. This is a number so large it is almost meaningless. Let's try to put it in context. It is roughly equivalent to the total electrical energy consumption of a medium-sized city for an entire year, released in less than a millionth of a second. This is the primary constraint of the system. All the destruction we have discussed is a consequence of the planet's surface systems trying to absorb and dissipate this colossal, instantaneous injection of energy. The consequences are a direct function of the parameters of this energy release. The temperature of the fireball, which is millions of degrees, dictates the spectrum of the thermal radiation. The speed of the expansion dictates the pressure of the blast wave. The nuclear reactions themselves dictate the type and quantity of the radiation that is produced. By looking at the event through this purely physical lens, we can see it as a thermodynamic problem. The city is a complex low-entropy system, a highly ordered arrangement of matter. The nuclear detonation is a massive, high-entropy event. The interaction between the two is a violent and irreversible process of the universe tending towards disorder. This perspective allows for a kind of sensitivity analysis. If we were to change the parameters, for example, if we increase the yield to 1 megaton, the energy release increases, and the radii of destruction expand accordingly. If we were to change the detonation from an air burst to a ground burst, the partition of energy would change. A ground burst would put less energy into the blast wave, but it would create a much larger crater and vastly more radioactive fallout, as it would vaporize tons of earth and debris. This energy flow archetype is powerful because it is the root of the causal chain. Every effect we have discussed, the fire, the wind, the radiation, the systemic collapse, is a downstream consequence of this initial, unimaginable release of energy. It is the engine that drives the entire destructive machine. The ultimate implication is a lesson in scale. The forces that hold the atomic nucleus together are millions of times stronger than the chemical forces that hold molecules together. By unlocking that nuclear force, we have introduced an energy source into our world that is out of all proportion to the structures, both physical and social, that we have built. Our cities, our bodies, our ecosystems are all evolved and designed to function within the gentle energy flows of the sun and of chemical reactions. The nuclear event is the violent intrusion of a stellar-scale energy flow into that delicate terrestrial system. The destructive mismatch is the very heart of the story. The sensitivity of the urban and biological systems to this energy injection tells a sobering story about trade-offs. The very complexity and efficiency of our civilization make it incredibly vulnerable. A simple agrarian society is far more resilient to this kind of shock, as it has less complex infrastructure to be destroyed. There is a fundamental trade-off between efficiency and robustness. Our modern world has been built to optimize for efficiency. The nuclear event reveals the catastrophic downside of that design choice when faced with a sufficiently large shock. The multiple plausible mechanisms of destruction, fire, blast, radiation, are not competing theories. They are the different facets of a single, unified thermodynamic event. The uncertainty is not in the total energy released, which is a known quantity. The uncertainty is in the precise way that this energy would interact with the infinitely complex and unique system of a particular modern city on a particular day. The uncertainty budget is in the messy, unpredictable details of the interaction, not in the fundamental physics of the source. The story of the atomic bomb is not just a story of physics and engineering. It is a story that has been deeply woven into our culture for 3/4 of a century. The image of the mushroom cloud has become a universal symbol, a cultural archetype for apocalypse and for humanity's capacity for self-destruction. Older narratives, from the myth of Icarus flying too close to the sun to the story of the Tower of Babel, have mapped this same pattern. The dangers of hubris, of humanity acquiring a power that it is not wise enough to control. The atomic bomb is the ultimate technological manifestation of this ancient fear. During the Cold War, this story was told in many ways. It was told in the civil defense films that taught children to duck and cover, a narrative that attempted to frame the unthinkable as a manageable, survivable event. It was told in stark, terrifying films like The Day After and Threads, which stripped away the euphemisms and forced a generation to confront the visceral reality of a post-nuclear world. It was told in the stories of the atomic soldier, the military personnel who witnessed the atmospheric tests and were sworn to secrecy, their bodies carrying the silent memory of that exposure. It was told in the art and literature of the time, in the novels of Nevil Shute and the poems of Allen Ginsberg. These cultural narratives act as a bridge between the abstract, technical reality of the weapon and its felt human meaning. They are the ways we, as a society, have tried to process this new and terrible knowledge. This cultural lens reveals a deep ambivalence. On the one hand, the bomb was a symbol of national power, of scientific achievement, of security through strength. On the other hand, it was a symbol of profound anxiety, of a future held hostage, of a world that could end in an instant. Our exploration tonight, in its own quiet way, is another telling of this story. It is an attempt to use the language of science and systems to build a new kind of narrative, one that is not based on fear or political ideology, but on a calm, methodical, and evidence-based understanding of the physical reality. By holding these cultural stories alongside our scientific model, we can see that we are not the first to grapple with this subject. We are part of a long, ongoing conversation, a multi-generational effort to make sense of the moment when humanity unlocked the power of the stars and brought it down to Earth. We have followed the threads of energy, from the initial flash of light to the enduring poison of fallout. We have seen the city as a physical structure and as an interconnected system, and we have modelled its catastrophic failure. We have placed the event in its historical and cultural context. Now, we approach the final turn. We are about to move from a detailed analysis of the event's components to a final synthesis. We will reframe the binary of survivable versus unsurvivable into a more nuanced continuum of systemic collapse. We will integrate the physical destruction with the informational and social collapse. This is the moment where we step back and view the event not as a series of discrete effects, but as a single, holistic transformation of a world. It is the moment we bring all the pieces of our solemn thought experiment together. The turn we must now make is to move from the binary of destruction versus survival and reframe the event as a continuum of systemic transformation. An either-or framing is not useful. The question is not if the city survives, but in what state it is left, and what that new state means. Let's replace the binary with a spectrum of states. On one end, you have a functioning modern city, a complex high-energy information-rich system. On the other end, you have radioactive rubble, a simple low-energy information-poor system. The nuclear event is a catalyst that forces a rapid, violent transition along this spectrum. The location of a particular point in the city on this spectrum is determined by its distance from ground zero. Close to the center, the transition is total and instantaneous. The system is pushed all the way to radioactive rubble. Further out, the transition is partial. A building might remain standing, but without power or water, it is no longer part of a functioning urban system. It is a stranded asset in a broken network. This reframing allows us to translate the abstract physics into lived choices, or rather, the removal of them. For the inhabitants, the transition is experienced as a catastrophic reduction in complexity and agency. A person in a functioning city has access to a vast network of services that support their life. After the event, a survivor is thrown into a radically simplified world, where the only choices are about the immediate, brutal necessities of survival, finding water, shelter, and safety from radiation. This perspective widens our model beyond the single city. A large-scale nuclear exchange is a global-scale transition. It would push our entire planetary civilization along this spectrum, from a complex, interconnected high-energy state to a much simpler, fragmented, and lower-energy state. The turn is the realization that the nuclear event is not just an explosion. It is a state change catalyst. It is an act of enforced, instantaneous simplification. It takes a complex system and brutally, efficiently, reduces it to its component parts, stripping away the connections and the information that made it a coherent whole. This reframing helps us to understand the true nature of the threat. It is not just about death and destruction, as horrific as that is. It is about the potential for the irreversible collapse of the complex systems that we call civilization. The recovery is not about rebuilding the hardware. It is about the near impossible task of rebooting the entire operating system after a catastrophic crash. Let's attempt our first pass at a grand synthesis, integrating all the evidence tracks into a minimal, coherent model of the event. We will connect the microscale physics to the macroscale systemic collapse. Our model begins with a single, irreversible event, the detonation of a 300 kiloton thermonuclear device 1,800 meters above a city. This is the initiating perturbation. In less than a second, this event converts a small amount of matter into a quadrillion joules of energy. All subsequent effects are the result of this energy interacting with the environment. This energy propagates outwards in three primary forms. First, the thermal pulse travels at the speed of light, igniting thousands of fires in a radius of several kilometers. This is the initial attack on the city's material integrity. Second, the blast wave travels at the speed of sound, delivering a devastating wave of pressure that systematically dismantles the built environment, creating a vast field of rubble and fanning the flames. Third, a wave of prompt radiation poisons the area closest to the detonation, while the radioactive fallout creates a much larger downwind plume of long-term contamination. These three physical blows are delivered almost simultaneously. The city, as a complex system, cannot withstand this multi-pronged assault. The physical destruction of its hardware, the power plants, water mains, and communication towers, triggers a cascading, systemic failure. The power goes out, the water stops, communication ceases. The city's metabolism, its circulatory system, and its nervous system all fail at once. The damage is amplified by positive feedback loops. The blast wave creates fuel for the fires. The failure of the water system prevents the fires from being fought. The fires merge into a firestorm, a self-sustaining meteorological event that incinerates the city's core. The collapse of the city's informational DNA, its blueprints, its digital records, its skilled population, makes any coordinated response or rapid recovery impossible. This is the micro to macro connection. The nuclear physics of a single atomic nucleus, multiplied trillions of times in a chain reaction, creates a macroscopic fireball. The energy from this fireball, interacting with the materials of a single house, causes it to burn and collapse. The collapse of 1 million houses, combined with the failure of their connecting infrastructure, leads to the death of the city as a functioning entity. The model is one of synergistic destruction. Each effect magnifies the others. It is a story of a system being pushed so far and so fast from its stable equilibrium that it cannot recover. It is a forced transition to a new, stable state, a cold, dark, silent, and radioactive ruin. This synthesis avoids triumphalism or sensationalism. It is a sober, physics-based account of a process. It shows how a single, technological act can trigger a complete and catastrophic failure of the complex, interconnected systems, both physical and social, that constitute a modern city. A robust synthesis must also reconcile the counterpoints and explicitly acknowledge the remaining uncertainties. This second pass is about holding our model with humility and mapping its limits. First, let's reconcile our model with a survivable limited event countermodel. Our synthesis does not deny that a single steel frame building might remain standing, or that a person in a deep basement might survive the initial blast. It reconciles the two views by focusing on the systemic nature of the collapse. The survivable event model focuses on the resilience of individual components. Our synthesis shows that even if some components survive, the destruction of the network that connects them leads to the failure of the system as a whole. A surviving skyscraper without power, water, or access is a tomb, not a sign of the city's resilience. A survivor who emerges into a world of fire, rubble, and fallout is not a testament to survivability, but a participant in a new and desperate crisis. So, the reconciliation is this. Individual survival of the initial event is possible, but this does not equate to the survival of the city as a functioning social or technological entity. Now, let's explicitly name what remains unknown. The single biggest uncertainty is the human factor. How would large populations of modern urbanites, stripped of all the technological supports of their society, actually behave? Would there be cooperation and mutual aid, or a collapse into violent competition for scarce resources? History offers conflicting examples, and no true analogue for this specific scenario exists. Our models of social collapse are far more speculative than our models of physical collapse. The second major uncertainty lies in the global, systemic effects of a large-scale exchange. The nuclear winter hypothesis is a robust theory. but the precise magnitude of the cooling and its specific effects on global agriculture still have significant error bars. The potential for other, unforeseen tipping points in the Earth system to be crossed is a known unknown. Could a nuclear war trigger a collapse of the ocean circulation, for example? We don't know for sure. The next steps for research in this field are, thankfully, theoretical. They involve refining our computer models, using more powerful supercomputers to simulate the interaction of the blast and fire with ever more detailed models of urban environments. They involve further study of our modern infrastructure's vulnerability to EMP. They involve deeper sociological and psychological research into human behavior during extreme disasters. Our model is the best description we can create from the available data. It is a story of a tightly coupled system where the failure of one component rapidly leads to the failure of the whole. The major unknown is not in the physics of the bomb, but in the chaotic, unpredictable, and complex response of the two most complex systems we know, the global climate and human society. To make this synthesis tangible, let's walk through it as a lived experience. We will use a second-person narrative to place you within the system as it fails. You are in your home in a residential neighborhood, 5 kilometers from the city center. The first thing you experience is an impossibly bright flash of light, brighter than the sun, that fills the room, even with your back to the window. The light is so intense it momentarily whites out your vision. For a few seconds there is a strange, profound silence. You might notice the heat from the thermal pulse on your skin. Then the sound arrives, but it is not just a sound, it is a physical blow. The blast wave hits the house with the force of a physical impact, accompanied by a deafening, continuous roar. The windows shatter inwards. The walls of your home flex and then disintegrate. The world is a vortex of noise, pressure, and flying debris. You find yourself in the ruins of your home. It is now a pile of splintered wood and broken drywall. The world outside is unrecognizable. A powerful hot wind is blowing, fanning the small fires that have started all around you. The sky is dark with smoke and dust. You are alive, but you are now inside a new system, a new world with new rules. The rule of law is gone. The rules of infrastructure are gone. The only rules that matter now are the rules of survival. Your first priority is shelter. The ruins of your house are unstable and burning. You need to find a more stable structure, perhaps a basement. Your second priority is water. The taps are dry. You do not know if the water in the pipes is safe to drink. Your third priority is the invisible threat, the fallout. You know from old stories that a rain of radioactive dust is coming. You must find shelter that can protect you from the gamma rays it will emit. You are now a part of a new system, the post-nuclear survival landscape. Your connections to the old system, your job, your bank account, your social network, are severed. Your new connections are to the physical realities of your immediate environment, the stability of the rubble, the direction of the wind carrying the fallout, the location of a potential source of stored water. The causality is clear. The physics of the bomb created a new physical environment. This new environment dictates a new set of survival imperatives. Your complex life as a citizen of a modern city has been brutally simplified to the life of a scavenger in a toxic ruin. The synthesis is not an abstract model. It is the lived reality of a world where all the complex systems that supported you have been switched off at once. This deep and sobering exploration of a planetary-scale threat is not meant to leave us in a state of helpless despair. Instead, it can be translated into small, testable practices of attention and agency that can enrich our experience of the world we actually inhabit. These are not prescriptions, but invitations. The first practice is to appreciate complexity. Our thought experiment has been a story of a complex system collapsing into a simple one. We can practice in our daily lives noticing and appreciating the immense, invisible complexity that supports our existence. The next time you turn on a light switch, take a moment to contemplate the vast, intricate network of power plants, transformers, and wires that makes that simple act possible. The next time you buy food at a store, consider the global supply chain of farms, transportation, and logistics that brought it to you. This is a practice of seeing the hidden web of interdependence that underlies modern life. A second practice is to value maintenance. A nuclear event is a story of catastrophic failure. The opposite of this is the slow, patient, and often unglamorous work of maintenance. We can practice valuing this in our own lives and communities. The work of repairing infrastructure, of maintaining social trust, of tending to institutions, of educating the next generation. This is the work that holds the complex systems together. It is the constant, low-level effort that prevents collapse. This practice is about shifting our focus from the excitement of new creation to the quiet, essential dignity of stewardship. A third practice is to cultivate non-panicked awareness. Our journey has been a deliberate exercise in looking at a terrifying subject with calm and methodical attention. We can apply this to the risks and challenges in our own lives and in the world. Instead of reacting with immediate fear or avoidance, we can practice asking, what are the mechanisms at play here? What are the systems involved? What are the feedback loops? This is not about being cold or unfeeling. It is about building the emotional and intellectual resilience to engage with difficult realities constructively, rather than being paralyzed by them. These small, local-first practices do not require us to solve the problem of nuclear weapons. They are about internal shifts in perspective. They are about using the stark lessons of this thought experiment to live with a greater sense of gratitude for the complex, fragile, and beautiful world we have, and a greater appreciation for the quiet work that is needed every day to keep it. What does the future hold for this technology and for the world it has created? We can only engage in bounded speculation, mapping plausible scenarios based on the dynamics we have observed. In the near term, the open questions revolve around proliferation and stability. Will more nations develop nuclear weapons, making the global system more complex and potentially more unstable? Or will the international non-proliferation regime hold, or even be strengthened? What is the impact of new technologies, like cyber warfare or artificial intelligence, on the stability of nuclear command and control systems? These are the urgent questions for the coming decades. Our confidence in any specific outcome is low. The system is too complex and dependent on human choices. In the longer term, we can imagine two diverging pathways. One is a future where the lessons of the Cold War are forgotten, where arms control treaties unravel, and a new multipolar nuclear arms race begins. In this scenario, the risk of nuclear use, either by accident, miscalculation, or design, would increase significantly. This is a future of heightened chronic existential risk. The other plausible scenario is one of gradual, painstaking progress towards disarmament. In this future, the international community, driven by a shared understanding of the catastrophic consequences, slowly builds a more robust system of verification, trust, and international law that leads to the eventual elimination of nuclear weapons. This is a future of hope, but one that requires immense political will and multi-generational effort. The philosophical boundary here is the question of human nature. Are we a species that is ultimately doomed to use the technologies we create, or are we capable of developing the wisdom and the political structures to manage our most dangerous inventions? The past 75 years offer evidence for both arguments. We have created these weapons and come perilously close to using them on several occasions. But we have also, so far, managed not to. The future direction is not predetermined. It is a choice. The knowledge of nuclear physics is a permanent part of our world. The future will be defined by how we choose to live with that knowledge. The thought experiment we have conducted is a tool for clarifying the stakes of that choice. It does not tell us which future will happen, but it tells us, in stark, physical detail, what we are choosing to avoid. How do we process the emotional weight of this knowledge? What is the felt meaning of this solemn thought experiment? The goal is not to arrive at a state of fear, but at a state of profound and sober clarity. The first emotional reframe is a shift from abstract anxiety to concrete understanding. The vague, undefined fear of the bomb is often more paralyzing than a clear-eyed view of the actual event. By walking through the physics step by step, we demystify the event. We replace the monstrous, unknowable boogeyman with a set of understandable, if terrifying, physical processes. This knowledge, while grim, can be empowering. It allows us to ground our feelings in reality, rather than in imagination. The second feeling this journey can cultivate is a powerful sense of connection to our shared humanity and our shared history. The nuclear age is a story that belongs to all of us. It is the central, defining technological and political reality of the last 3 generations. To understand this story is to understand a key part of the modern world. It connects us to the scientists of the Manhattan Project, to the decision-makers of the Cold War, and to the millions of ordinary citizens who have lived their entire lives under this nuclear shadow. It is a heavy inheritance, but it is our shared inheritance. Finally, and perhaps most importantly, this exploration can lead to a profound appreciation for the state of non-event that we currently inhabit. We can learn to see the ordinary, peaceful day not as a given, but as a precious and actively maintained accomplishment. The fact that these weapons have not been used in conflict for over 75 years is not an accident. It is the result of tireless work by diplomats, activists, and leaders. To understand what a nuclear detonation is to understand the profound gift of its absence. It can transform our perception of the everyday, the quiet hum of a functioning city, the simple pleasure of a sunny day, the trust that allows society to function. These are not mundane. They are the hallmarks of a world that has so far chosen a different path. This emotional reframe is not about finding happiness in a dark subject. It is about finding a quiet, stable, and deeply appreciative place from which to view the world as it is. It is a calm born, not of ignorance, but of understanding. We have arrived at the edge of our model. We have followed the chain of causality from the subatomic to the planetary. We have used the tools of science to build a plausible, evidence-based picture of a nuclear event. But here, at this boundary, science falls silent. The data can tell us what would happen. It cannot tell us what it means. Our scientific model is a story of physics. It is a narrative of energy, pressure, and radiation. It is ethically neutral. It describes the demolition of a building with the same dispassionate language it uses to describe the functioning of a star. But we are not ethically neutral beings. We are the ones who must confront the meaning of this knowledge. The moment we ask, is it right for humanity to possess this power? We have crossed the philosophical boundary. The moment we ask, what are our responsibilities to future generations? We have moved from the realm of physics into the realm of ethics. Science can inform these questions. It can give us the clearest possible picture of the consequences of our actions, but it cannot answer them for us. The choice to build these weapons was a human choice. The choice to maintain them is a human choice. And the choice to dismantle them would also be a human choice. These are choices based on values, on fears, on hopes, on our conception of what it means to be human and to live together on a shared and fragile planet. Our journey tonight has been an attempt to provide the firmest possible scientific foundation for that ethical contemplation. We have held the difficult questions open, not to solve them, but to understand their physical grounding. The rest of the conversation is not one of science, but of conscience. It is a conversation that belongs to all of us. As we conclude, let's hold 2 final frames for this knowledge, 2 parallel ways of making sense of our precarious situation, both rooted in humility. The first is the frame of emergence and complexity. From this perspective, our global civilization is a complex adaptive system. It has emergent properties, like our technological capacity and our interconnected global economy. But this complexity also creates new emergent risks. Nuclear weapons are a perfect example. They are a product of the system's complexity, and they now represent a systemic risk to the entire system. In this frame, the challenge is one of managing a complex system that has developed a powerful capacity for self-destruction. The future is not predetermined. It is an emergent outcome of the countless interactions and choices made within the system. The humility here comes from recognizing that we cannot fully predict or control a system this complex. Our best hope is to foster resilience, reduce risk, and learn to navigate the immense power that our own complexity has given us. The second frame is that of anthropic responsibility. This frame starts with the simple, profound fact of our existence. We are, as far as we know, the only species on this planet that has developed both a consciousness capable of understanding the universe and a technology capable of destroying itself. From this perspective, our existence is not just a random outcome, but a moment of profound cosmic significance. It bestows upon us a unique and heavy responsibility. We are the universe's way of becoming aware of itself, and we are also the custodians of that awareness. The challenge in this frame is a moral and even a spiritual one. It is the challenge of developing a wisdom that is equal to our power. The humility here comes from the recognition of our unique and precarious place in the cosmos. We are the holders of a very fragile flame. These two frames are not in conflict. They are different languages for describing the same predicament. Whether we see ourselves as managers of a complex emergent system or as custodians of a fragile cosmic consciousness, the conclusion is the same. We live in a world of immense technological power and profound existential risk. The knowledge of what a nuclear weapon is and what it does is not just a scientific curiosity. It is a central piece of the puzzle of what it means to be human in the 21st century. And so, we bring this journey to its final destination. You, here, now, inside this system. This thought experiment is not about a distant, abstract threat. It is about the world we inhabit, the systems we depend on, and the choices that shape our collective future. You are a participant in this system. The peace and stability of your daily life are maintained by a vast, complex, and fragile web of international agreements, political structures, and technological systems that have, for now, kept the nuclear genie in its bottle. You're not an outside observer of this system. You are a citizen of it. This recognition of personal belonging is not a call for a specific action. It is an invitation to a state of awareness. It is the agency of the informed citizen. To understand the stakes, to grasp the physics, to appreciate the systemic nature of the risk, this is the foundation from which all meaningful action grows. The story we have explored is a dark one, but the purpose of telling it is not to create darkness. It is to appreciate the light, the ordinary, everyday miracle of a world at peace, of a city that is functioning, of a life that can be lived without constant fear of annihilation. This is the precious reality that this thought experiment throws into sharp relief. You belong to this system. You belong to this historical moment. The choices we make collectively in the coming years and decades will determine which of the plausible futures we have discussed will come to pass. This is our shared challenge and our shared responsibility. We began with a quiet question in a quiet room. We have travelled through the heart of a man-made star, ridden the supersonic shockwave, and navigated the toxic landscape of a ruined world. We have done so not for the thrill of horror, but for the sake of a difficult and necessary understanding. We have built a model, step by step, of what would happen if a modern nuclear weapon were detonated over a city. We have seen how the initial release of energy would trigger a cascade of destruction, how the thermal pulse, the blast wave, and the radiation would act in concert to not just damage the city, but to cause its complete systemic collapse. We have seen how the very systems that support life can be turned into engines of their own destruction. We have re-asked our core question: what would it be like? It would be a transformation of the world into a hostile alien planet, a world where the fundamental conditions for life and civilization have been removed. And now, at the end of this journey, we are left not with a simple answer, but with a profound and heavy clarity. The purpose of this thought experiment is not to conclude that the world is doomed. It is the opposite. It is to understand, in the most concrete and physical terms possible, what is at stake. It is to understand what the generations before us have successfully managed to avoid, and it is to understand what our generation and the generations to come must continue to work every day to prevent. As we come to the end of our time together, I want to offer my sincere gratitude. Thank you for your willingness to engage with such a difficult and somber topic. It takes a certain kind of courage to look at these realities clearly, and your focused attention is the most valuable thing you can offer. This shared journey is a small act of collective sense-making in a complex world. If you have found this calm, methodical approach to be of value, I invite you to help it find others. There is no urgency. A simple share, a comment, or a quiet recommendation are all ways of contributing to a wider conversation based on understanding rather than fear. Thank you for being a part of this quiet community of inquiry. And so, we let the model dissolve. We let the grim images of our thought experiment fade. We release the tension of this difficult subject. The purpose was not to leave you with a feeling of dread, but with a renewed and deepened appreciation for the ordinary, profound peace of this present moment. The questions remain, as they should. How do we live wisely in a world that contains such power? How do we build a future that is safe from our own worst inventions? These are not questions with easy answers. They are the work of a lifetime, the work of a civilization. Our journey tonight was a small contribution to that work, an act of bearing witness to the physical reality that underlies the political one. Let what remains not be the fear, but the clarity. Let it be the quiet resolve to be an informed and engaged citizen of this fragile world. The story is a heavy one, but in understanding it, we become more capable of carrying it. Now, return one last time to the simple reality of the room around you. Feel the air on your skin. Listen to the quiet sounds of your environment. You are here. You are safe. The world is, for now, intact. The materials of your room, the wood, the glass, the metal, are stable. Their molecular bonds strong and secure. They are not being subjected to a stellar heat or a supersonic pressure wave. Their quiet integrity is a gift. The air you are breathing is clean and life-giving. It is not filled with smoke or radioactive dust. Its familiar composition is a testament to the vast, resilient, and beautiful biological and geological systems that maintain our planet in a state that is hospitable to us. This is the final echo. The story of what could be serves to illuminate the precious reality of what is. The purpose of our dark thought experiment is to make the ordinary world shine with a new and profound significance. The quiet, functioning peace of this moment is not a trivial thing. It is the most valuable and fragile thing we have, and to feel that deeply is the true and final purpose of our journey together tonight.